All right, your second podcast on equilibrium is dealing with heterogeneous equilibria and Kp. So let's get started. First of all, heterogeneous equilibria, that's something to keep in mind. That means that things have different states of matter. They might have solids, liquids, gases, that kind of stuff. But when we write out the law of mass action to determine KEQ, one only includes gaseous substances and substances in solution. Solids and liquids are not included in the calculation of the equilibrium constant. So if you see here, we have A plus B yields C plus D. But we'll also notice that A is a solid and D is a liquid. Those are not going to be included in the law of mass action. But the law of mass action still has products over reactants, but only the ones that are either gases or in aqueous solution. So let's look and see what we got here. Notice we only included the C, and it's still raised to the power of 2, and we have the concentration of B raised to the power of 3. Notice we only included those that were in aqueous solution or gaseous substances. We did not include the solid or the liquid. Remember that when it comes to writing out chemical equations, that the physical state is very important of whether or not you include it in the law of mass action. All right, so now we're going to use partial pressures to determine the KEQ. This is not as straightforward as when we use concentrations. So Kp is what we call the equilibrium constant when we use partial pressures. This is different than KQ, or what some refer to as Kc, where that's the equilibrium constant using concentration. All right. Now there is a formula in order to convert these two back and forth from each other. I'm not going to go through this with you of how I derived this equation. If any of you want to find that out, just email me or just see me in class. But Kp is equal to Kc times parentheses RT to the power of delta N. Now the way we got this Kc times RT is from PV equals nRT, or our ideal gas law equation. Now when we do this, we have a delta N in here, and what does that really mean? It means the sum of the product coefficients minus the sum of the reactant coefficients. Now I know this might seem confusing, so let's go through a sample problem with this. All right, at 300 Kelvin, the equilibrium partial pressures of each of the gases listed above are in the table below. Our job is to calculate Kp and then eventually Kc. So we're going to use the law of mass action, but we're going to use the partial pressures that we see here in the table. That's not calculating Kc, that's calculating Kp. So let's take a look. Notice I've just put the partial pressures where they belong in the law of mass action and raised them to the respective coefficients there. We have 3.0 for C, we have 5.0 for A, and we have 4.0 for B. When we do this calculation, we get a Kp equal to 0.028. So now what we want to do is we want to convert that into Kc and solve the second part of this question. Remember that our equation is Kc equals Kp times RT to the delta N. So when we look at this, our Kc is equal to our Kp, which is 0.028, and then we multiply it times that RT. Notice the R is 8.31, which matches our Kpa up there, our R value for Kpa, and we multiply it by its temperature. And then notice that we've raised it to the power of -2. All right, that's because the products, if you look at their coefficients, it only has a 2 in front of the C, and we're going to subtract off the sum of the reactant coefficients. A has 1 and B has 3. So when we add those together, we get 4. So products 2 minus reactants 4 gives us a -2 for our exponent. And when we multiply all that out, we get a Kc, or a Keq, equal to 4.5 times 10 to the -9th. Now that shows that that reaction lies very far to the left and that the reactants are heavily favored.